She is from BIT Mesra, Ranchi, Jharkhand, from CSE department. She joined BIT Mesra in 2003. Presently, she is working as associate professor in the department of CSE. She did. She did her BTech degree, BE degree in electrical engineering from BIT Sindri, and followed by ME degree in software engineering from BIT Mesra, and further she did her PhD from BIT Mesra itself. She has vast teaching knowledge of nearly teaching experiences 17 years and research experiences 12 years. Her research area is many diversified field, among them few which are related to computer science, and just telling about that: Internet of Things, cyber physical system, wireless and ad hoc networks, software design and testing, database modeling. Along with that, her publication, I think more than 25 publications, reputed SCI journals are there. Her conference proceeding, 6 or more conference proceeding, few conferences are there. She organized, I think, 10 or 12 conference paper. She has more book chapters, 5, 6, minimum 5, 6 book chapters should be there, I think. And she is the member of ISTE. Along with that, she is presently guiding 3 or 4 PhD candidates. And she is the editorial board member of Journal of IoT Application for Smart City. Along with that, this madam has handling so many institute, many involved in many institute activities along with departmental activities. So her topic is the role of IoT in sustainable infrastructure. So with this, I'm giving the charge of madam to please proceed, ma'am, with enlighten your words for our faculties. Please, ma'am.
Thank you, sir. Okay, so I am Dr. Itu Snigdh, and I've already been introduced. Thank you, sir, for that. So I'll directly come down to the topic of discussion today, and I've just tried to map 3 diverse domains. The role of data, because IoT is nothing without the data that has been collected, IoT as such, and the sustainability in infrastructures, which is the current growth that we are seeing. Okay, so when we talk about sustainable infrastructure, up till now we have seen a tremendous growth in infrastructure development, and we hear so many different jargons and keywords like smart city, automated buildings, etc. Similarly, we have seen a growth in automation because of the advancement of technology, and this automation is something that is going to be generated or is something that can be realized with Internet of Things applications. So these two are very different technologies, two very different terminologies which are going to be connected to today. So what the main objective of today's discussion is: how at all are we going to explore Internet of Things applications to make our infrastructure robust for a sustainable future. Okay, so I believe that we are all aware of sustainability, and the topic of discussion is of 3, as I said, is across 3 domains. One, I'll be discussing about the IoT fundamentals and the architecture, and then I'll be talking about what are the objectives of sustainable infrastructure that can be realized with IoT, and finally I'll be connecting our IoT to sustainability. So I'll be just discussing where we can map IoT with automation. Okay, so I hope my screen is visible to all of you.
Yes, ma'am, it's visible.
Okay.
It's visible, ma'am.
Yeah, just a second. The slides were not moving. Okay, fine. So I start off with my discussion of smart. So what do you mean by smartness? Whether it is related to people or what or who, whether it is related to device or people. So I'll just be outlining the first the definition of a smart. Why? Because we are always talking of automation and we say that we've got a smart device, we've got a smartphone, it's a smart building, it's a smart city. So coming down to those terminologies, we first need to understand what smart is. So the first question is how to define smartness. So what do we actually want is, if I, what do we actually want is, I'll just make a few inputs out here and I'll say that the first thing that a smart person or a device or a thing needs to do is perceive the environment. So this is perception as our sensory organs. So this is something that is inherent to a smart device. The other thing that we require for smart is that I need to have a knowledge base. I need to have a knowledge base, and this has to be populated on past experiences. Okay, so if I have to have a knowledge base, I need to have a data repository, or I need to have a database where I'm going to collect these data and I'm going to structure this data and derive certain information on the basis of this data. Okay, similarly, one more essential part that we find out in a smart device is that it requires an accurate interpretation, right? It requires an accurate interpretation on the basis of collected data. Fine. Now, what do we require at the output side? So this becomes basically the input that we, or the characteristics of the system that has to be inherently be present. Okay. What do we expect out of a smart device? The first expectation of a smart device is that it should have a decision making capability. Okay, so this is the first output that I require. This is the first thing that I want my smart thing or a device or a person to do. The second thing is that I should be able to communicate, right? I should be able to ability to communicate for taking action, right? So these are the two outputs that are going to be expected out of a smart device. Okay, so the first thing that from this the picture is clear as to what we need to put in an IoT application so that we are able to achieve decision making capability and we are able to communicate for taking action. The communication becomes essentially important because not all tasks will be able to be accomplished by the same device. So we need a network of devices or we need actuators to actually do the performance of that action. Because we are and the main agenda of today's discussion is that we need to have sustainability as the prime focus. So I'll not go into the definition of sustainability in just layman terms. I'll just try to explain that sustenance is being able to use this resources currently and to be able to reserve something for the future, for near future use as well. So I do not need to exhaust my resources as of now. I need to utilize the resources with the most optimal manner so that the resources are long lived. So as per the layman understanding of sustainability, this is the definition. Now, if I have to incorporate this particular thing with an infrastructure, we'll be discussing that in the next few slides, right? So now coming down to, once we've discussed about our what do we expect out of a smart device is how are we going to integrate it. So the next thing that we can move on to is what are the technology enablers of an IoT. So as I said that I need it to decide, I need it to have an knowledge base. I need it to be structured, and I need to be able to infer knowledge from the collected data, take action, or instruct someone else to take action. Okay, so based on these 4 5 things, we have 5 technology enablers for IoT. Okay, the first technology enabler is a wireless sensor network, because we said that perception is critically important. So this is a wireless sensor network that comes into picture. It is the most fundamental unit of any IoT application. So whether we are going to be using it in context to a smart city, smart traffic monitoring, let's say climate monitoring, volcano monitoring, let's say convoys of vehicles, automated driving. So irrespective of what is the automated application, we are going to require a wireless sensor network. So the wireless sensor network is something that is going to be comprising of multiple small sensors, wherein the sensors are nothing but the elements that allow you to perceive the environment. So the first fundamental requirement was that if I am smart, I need to perceive the environment. Perception of the environment is clear. So the sensors are the elements that are going to enable us to perceive the environment. Whatever the sensors collect in the whether they are singular or they are working in a collaborative computing model, okay, they need to communicate it to a particular repository, which may be a sync node or a server, or it may use the internet resources, internet connectivity, to directly load it into the machine of the end user. Okay, so basically the role or the function of a sensor is to collect data and transmit it to via network resources or via a wired connection to a particular repository, which we call essentially a server. So that is the role of a WSN. The WSN is going to collect data. Okay, next we come down to the machine to machine architecture, because the smart device may or may not be able to take an action. Okay, so it requires to be able to communicate or give instructions to some other device to take the appropriate action. We require our machine to machine architecture. So this is the diagrammatic representation of a machine to machine architecture, in which this depicts the actual uh, physical device that is collecting data and doing the analytics, and it is being used to analyze at a farther machine, which may be a cloud, stored at the cloud, or it may be at some physical server, which is doing the analytics and then again sending it as a feedback that tunes the performance or efficiency, or it commands the devices to take a particular action. So this is nothing but these devices. These are physical devices that are going to collect the data, send it to the server. The server is going to analyze the data and send the feedback. I'll take an example of a conveyor belt. Okay, so let's say a conveyor belt in a steel rolling machine. Okay, so at one particular time, it needs to perform a laser cut on the steel roll. So the conveyor belt is going to move at a particular speed, right? And the automated process is going to fire the laser gun at a one particular instant of time with certain precision. Now, dependent on the type or the quality or the grade of the steel, the precision is going to vary. So if this machine, if the automated device is not able to cut that steel roll properly, it will send in the actual the image is going to be sent whether it was a precise cut or not, and then it is going to be modulated, or the fineness in the cutting of that steel roll is going to be performed. So for that, I require a machine to machine architecture. These are two machines. The computer system is also a machine, and the sensor devices which are communicating are also machines. So it is absolutely a machine to machine sort of a communication. So this is the next element that is essential for any IoT application. Okay. When we come down to how at all are we going to collect the data, or how we are going to go about with analyzing that data, we have artificial intelligence, machine learning algorithms that are going to be working on the data for performing that analysis. Okay. It's not necessary that all the analysis has to go back to a remote server or to a wired server. There are certain analyses that can be done at the device level itself. Okay. So because of the type of application that we are expecting, we have machine learning, full-fledged machine learning algorithms for end devices or high-end devices. And we have facilities like tiny ML that can be embedded with the device in the chip for doing small analytical applications as well, right? So basically AI is something that is just going to write an if then else rules on which you can put it on a chip, or a high end machine can be doing that. Okay. The third part is our semantic technology. As I said, that smartness to a device or smartness in a person comes down on its decision making capacity. Basically, the decision making capacity is something that allows you not to repeat the same mistakes again, or to be able to make better and better decisions with each passing day. So this decision making capacity can only be improved if you are having a knowledge base that you are populating on the basis of past experiences. So on the basis of the feedback and the decisions that you have taken, we can have a large repository, right, which we need to understand. So semantic technology just tries to map the structured and unstructured data, because every sensor is going to generate a very large volume of data. So semantic technology is used to map that textual or image data to be able to allow inference rules over that particular data. So we require an semantic technology to infer from the existing data. On the basis of the inferences, the AI model is able to suggest a particular action or take a certain action. Now, who is going to supply data to this particular model is our wireless sensor network. How is it going to be communicated? It is going to be communicated using a machine to machine architecture. Who is going to take an action? It is also going to be taken care by the M2M architecture. It's just like if the tank is full, the motor needs to be turned off and it has to happen automatically. So you need a relay. So it's as soon as the flow sensor is going to detect that the tank is full, the relay turns off the switch. And so because the relay is also a machine, the switch is also a machine, and the flow sensor is also a machine, we say that it is a machine to machine communication. Now, this makes us so now summarizing the and connecting it with smart infrastructure, we need to understand where IoT is going to be used when it comes down to a small application, that is smart infrastructure, right? So we already know that IoT is going to be made up of a vast network of physical devices. What are these devices? They may be sensors, they may be chips that are carrying the software, and there may be other technologies like buzzer, like relay, like AI models, like machine learning models, which allow them to collect and exchange data over the internet. What else do we need out here? We need a connectivity. We need to connect because it's a large network and there are heterogeneous devices. We need it to be connecting. What are the requirements of the connectivity? Is that because we are talking of automation and we need the device to perform in real time, because it needs to feel like a human is going to do that work, right? So you need that real time monitoring and control. So the connectivity needs to facilitate the automated process where you are going to transfer data, you are going to take in the feedback, you are going to control your processing according to the feedback. So you require a data driven decision making. You require connectivity for automating the processes as well as real-time monitoring and control. Okay. The basic architecture of IoT will comprise of four layers. Irrespective of what application we create, it will always be created in four segments. So the first segment or the lowermost tier in an IoT architecture is going to be about physical devices. So physical devices are going to be comprising of sensors and actuators. So both of these are nothing but machines. Okay. Then we need connection. We need to connect the devices. We need to connect the device to the server. We need to transfer data from the device to the server and receive command from the server to the data. So you require connectivity for data transmission. The third thing that we essentially require is the middleware. So the middleware is nothing but the data processing and management. So we don't pass on, for example, in a fire alarm. Okay, so I can have a small fire alarm application in which the sensor is going to detect heat and smoke. Now, I can realize this solution with a cloud-based server, but the latency or the delay in which the heat and the smoke values are going to be transmitted to the cloud. And then the cloud analyzes that, okay, if this is the temperature and this is the amount of smoke, then fire is detected. And then it asks the fire extinguisher to turn on. It's going to be a delayed process. So I require a middleware that is going to do some local processing so that your IoT application is fast as per the requirement of the application. Okay. And then finally, the final layer is our application where the user is able to see what the IoT application is actually doing, just like our smart watches. So you have to have user interfaces and it is also going to provide you with analytics. Okay. Now, coming down to the architecture. So as I said that we've got three basic three-tier architecture. Okay, we have to stuff these four layers into this three tiers, right? So what do we comprise of? We comprise of devices, which may, and we comprise of sensors. There are sensors, low-end sensors, which will not be able to do the actuation part, and that's why we can separate the devices to with sensors. The sensors are just going to be used for collecting data. The devices like relays, like our software, computer systems, servers. Okay, so these are other physical devices that are going to be connected in the first tier. The second tier talks about of the sync node or the gateway if I have to transmit it to the cloud. So these devices are going to be low-end devices which require a device that is allowing for internet connectivity to a repository system, right? The last part, that is the systems, are nothing but the user systems which is going to visualize whatever actions are going to be performed by the physical devices. The edge is something that is going to sit near or parallel to the gateway, and it is solely used to reduce the latency. As I said, that for a fire extinguisher to get on, a fire alarm that we are having, we do not need it to reach the cloud, do the analysis out here, and then the command should go down. So at the buffer, it needs to be done somewhere in the middle. So when you are some perspective or some aspect of the cloud repository, if you are moving it towards the device, we call that edge based devices, right? So these devices are going to be sitting at the edge parallel to the gateway. Either the gateway is going to do a little bit of pre-processing or the edge devices are going to do the pre-processing. Okay, so the cloud is only going to be storing for larger processing capacity where you require high end analytics, then only the cloud should come into picture. Okay. Now, when we come down to infrastructure, if I need to implement a smart infrastructure, okay, I need to follow this schematic diagram. If we go about the IoT fundamentals, there are basically multiple architectures or multiple levels in which an IoT can be deployed. Okay, so if this is a basic line that divides local processing with the cloud-based processing. So in case there are 6 deployment models for an IoT application, smart infrastructure happens to fall in the 5th application. Okay. Now, what is deployment level 1? That is essential to be explained. In deployment level 1, we just have one node. We have just one device. There is just one singular unit. Okay. If this is one singular unit that is functioning and you are doing the processing locally, okay, then we can call it a IoT deployment 1. Okay, so the deployment levels increase as we increase the complexity of the design. So rather than having one device, now we have a collaboration of n devices. Okay, this device is nothing but the sensors and the actuators that we explained in the 4 layers. Okay. Now these sensors and actuators need to communicate to the gateway. Okay. And the gateway is going to be running a service that maps it into a packet so that it gets transmitted via the internet to a database. Okay. Now, if this controller service is going to just connect to a database itself, it becomes a singular unit, and now this becomes a local processing and level 1 deployment of an IoT application. Okay. Now, what do we see below are the routers or the endpoints. These routers are nothing but the intermediary devices, because when we talk about of sensors, and if we go about with so many physical applications, we need to we cannot they are not advanced enough to connect to the internet. We have seen the practical applications using Arduino. There are multiple microcontroller boards that may be adapted to connect to the Wi-Fi or to the internet, and there are certain boards that require specific microcontroller boards to connect to the internet, right? So basically these routers stand for those sub devices that are going to be helping these devices communicate or use the resource. The resource here is nothing but the components of the microcontroller units, okay, for which it is able to communicate, through which it is able to communicate to the end user, okay. So the devices here are pure sensors. The resources here are the high-end devices on which you install or you implant or you fix your sensors. So these are nothing but microcontroller boards. These microcontroller boards are going to run a controller service, okay? And you need a collaboration of each microcontroller board is going to be invoking or activating one service, and that's why you have a assembly of controller services if you have more number of devices, okay? Because these are multiple devices that are going to be communicating, these devices are going to form a network. And whenever we talk about of networks, they we talk about of multi-hop mesh sort of networks when it comes down to IoT applications. And that is why we require a coordinator that allows you to transmit intermittently, or we run scheduling algorithms just for saving of energy or reusing the bandwidth. Because whenever we talk about of IoT applications, they are usually low data rate, low power applications that we focus on. These are very small devices. These are miniature devices that do not have capacity to perform high computation. This is the basic constraint of a wireless sensor network or an IoT application, that the devices are going to be constrained because they are not having the capacity to do a large amount of computation, or they cannot have a wide, I mean, long distance communication neither they can do a large amount of storage. So you require multiple coordinators to sequentialize or schedule these devices to transmit their data in a time based manner, and there are certain algorithms that are purely focused on that. Okay, now what do we see out here is an observer node. This observer node is nothing but a controller that controls all the devices that are connected at the tier 1, at the device layer, and it is going to communicate via the internet to a REST through REST or WebSocket services to a cloud-based repository. So whenever we talk about um, communicating or developing a high-end application like a smart infrastructure, we cannot do local processing. So the processing needs to be done globally at the cloud so that you are able to access it from anytime, anywhere, and anything. So whenever we talk about of IoT, we say that the quality of an IoT is that it allows you to access or it allows you to interact with the system from any device at any time and from any location, right? So as soon as this constraint comes into picture, we need to implement the application on the cloud, right? So the cloud based application gives you this facility of anything, anytime, and anywhere. And that's why a cloud becomes essentially important for a smart infrastructure. Let me take an example of, let's say, a smart parking. A smart parking is a part of a smart infrastructure, and using your mobile apps, you can actually, from any location, you can identify whether a parking lot is free or not. And for that, what do we require? We require an app that is going to run on the system. We require an app that runs on our mobile phones, right? This app hooks up to a web, to a service that is facilitated by the internet. Okay, it does a little bit of analytics because it computes simple mathematics here. It finds the total number of parking lots. It sees how many, it detects how many cars are there in the parking lot, and it just does a small subtraction to identify whether there are vacant spots or not. There are similar examples like as in the case of hospital beds. Okay, in the case of hospital beds and other similar examples. Now, these analytics, whatever this app is going to access via the internet resources, is pre-stored in this database, right? How is this database going to get populated is that this coordinator is going to transfer it to the cloud, and this database is going to be sitting on the cloud, and that's how the data is going to be accessed by the app, right? So it is not a movement that happens top down. Please remember, these are the devices, these are the endpoints. One endpoint comprises of a device resource controller service. This is device number 2. This is another endpoint. It is also going to comprise of device, resource, and controller. So we are going to have n different devices. So because these n different devices need to be networked with each other, I need to have a coordinator node. We have so many algorithms of clustering based, right? We have layer based architectures, clustering architectures. So the same network architectures is going to come into play here. The main or the coordinator node is going to collect all the data from these endpoints and store it in the database. Where is the database located? This database is located in the cloud. Okay, now this cloud is connected to the application also. The application is run on an end user device, which does a little bit of analytics on the basis of the data that was stored in the device. So this is the structural representation of how an IoT application is going to be working. Okay, moving to the next portion of our, I hope any questions. I'll be okay to accommodate any questions we have here. Any doubts,
Ma'am,
anyone? Yeah.
ma'am, last at 3 o'clock we will do questionnaire.
Okay. Okay. Fine. Fine. Fine.
3:10 once your session will be over. Okay,
Okay.
ma'am.
Okay. Fine. Fine. So now moving on to the next portion of sustainability as such. So sustainability is something, as I said, that you need to use the resources currently as well as reserve resources for future use. So coming down to the theoretical aspect of sustainability, we study sustainability in three aspects: social, economic, and environmental. When we come down to our IoT applications, we typically are going to be focused on the environmental sustainability, because the topic of discussion that I've taken is smart infrastructure. And when we talk about of infrastructure as such, we energy and the emissions related to smart infrastructure contributes a lot to the degradation of the environment. So the sustainability for a smart infrastructure becomes important in context of the environment. So what are the indicators of sustainability? I'll not go into depth of sustainability. We'll just move on to that. Okay, we need to conserve our resources. So what are the steps that we can do to take care, to ensure sustainability using IoT applications? Okay, so the indicators of sustainability are in three ways. Either we are going to evaluate sustainability quantitatively: how many devices, what is the carbon footprint, how much are we able to reduce the CO2 emissions, and then we compute the efficiency. It can be qualitative, like our HVAC systems in case of automated buildings, where the quality of life of people are really important. Or it can be descriptive, as in we are storing data so that we are able to do some predictive maintenance or a predictive analysis for future use. That, okay, if we have consumed these many resources, we need to reduce the consumption of these resources for the next few months and things like that. So it's going to be, the indicators of sustainability are going to be dependent on what sort of analysis we want to do, and on the basis of the class of analysis that we do, we need to have an IoT based solution. So the IoT solution is going to be based on whether we want it to be quantitatively defined sustainability, or it wants to be defined qualitatively, where we find out the quality of life of people, as in pollution we want, so that relates to quality of life. Or it is going to be descriptive, wherein we are going to plan for future use, just like resources, coal resources and other natural resources, as in the case of smart grids. When it relates to infrastructure, whether we are doing a quantitative analysis or a qualitative or a descriptive analysis, it is only going to be working with two types of two factors, let's say. The first factor is going to be efficiency. We need to make our systems efficient, and we need to improve the performance. So these, when it relates to infrastructures, we are just going to have these two aspects to consider. Now, based on these two aspects, we've got our real world applications. Okay, so the real world applications, when IoT is related to a sustainable infrastructure, I've just taken four cases, and out of this, I'll be just taking one use case, that of a smart building, because that is the easiest to understand in this small, short span of time. So there are multiple real world applications that an IoT is going to use or employ. Among them, the first one, or the most frequently talked about, is that of smart grids. So when we talk of smart grids, we've got multiple functionalities for smart grids. So what is the agenda of having a smart grid is that I need to have an enhanced electrical grid that is going to utilize digital technology. It is going to allow two-way communication. In currently, we have just one-way communication. From the transmission lines, we get power into our homes. So we need to facilitate two-way communication, so that uh, we are able to optimize the generation and transmission and distribution costs, right? So what are the features of smart grids are that it should allow you two-way communication. We have advanced metering, real-time monitoring, and a demand response, a demand and a supply response. Where does sustainability come in? It does not come in anywhere. Okay. Sustainability only comes in this particular portion of smart grids. So sustainability has got nothing to with the advanced AMI infrastructure, the advanced metering infrastructure that we have. It has got nothing to do with sustainability. Neither two-way communication has got anything to do with sustainability. Sustainability, where we are using, we are generating and distributing energy, is only the sustainability is only achieved if we are able to control the amount of renewables into our system. How much can we integrate? How much of the renewable resources can we integrate yields a sustainable infrastructure? So what do we aim at? We aim at energy cost reduction. We aim at an enhanced reliability and an increased sustainability. So in this, so what is the main agenda here? What does smart grid do in the layman or in just one line context is that it allows consumer to have control over their energy consumption. So the end user can decide when to use a solar power converter or when to use the electricity that has been provided in the simplest of terms. Similarly, when we move down to water management, it just IoT can be used for pipeline management. How much, what quantity of water, whether there is a leak detection or not, can be used, can be implemented with the help of an IoT application. So water as a resource can be managed through multiple applications. One of the application is through leak detection so that we are not wasting water. It can also be used as a scheduled water supply dependent on the locality and the burden of water on that locality. So a highly populated area is going to get more amount of water rather than a less densely populated area. So these are water management fundamentals that can be taken care of with the help of AI and IoT systems. Okay. Then we move down to waste management. Waste management, we have multiple examples of an IoT based bin collection system wherein the vehicles that are going to dump these garbage bins will be routed in such a manner that they only go towards those garbage bins which are full, and it is not going to run through the entire city, thereby reducing the carbon footprint caused by the diesel consumption of those vehicles. So that is one option of waste management. Finally, coming down to smart buildings, because this is what I'm going to elaborate in today's talk, is that smart buildings, the basic functionality in a smart building is or the maximum amount of emission of CO2 in case of a smart building is in two ways. Either it is direct, and the direct emission is something that is decided by only the heating and the cooling of elements inside a building. Okay, so if we are able to control the heating and the cooling, okay, so we are able to reduce the total amount of CO2 emissions. Similarly, our smart buildings can have indirect and control indirect emissions with the help of materials and construction. So materials and construction for smart building is the purview of a civil aspect. It has got nothing to do with an IoT based solution. So an IoT solution is only going to work typically for a ventilating and automated airflow control inside a smart building or control of lighting and security. Okay, so there are three applications on which we are going to be focusing. Now, when we come down to how IoT is going to define, or how IoT is going to achieve what IoT is going to do with the infrastructure, is the first thing that it needs to optimize the resource use, because I need to have an optimal usage of the resource. So I need to monitor it and manage whatever I'm going to use so that I reduce the consumption and the loss. The next thing that the sustainable IoT based sustainability will be for enhanced operational efficiency. So I need to improve the efficiency by real-time data and predictive maintenance. Predictive maintenance is just one small sub part of the many things that you can do. Predictive maintenance basically reduces the total amount of time, or reduces the total failure proportion of a particular device functionality. So if I am able to do a predictive maintenance efficiently, I cut the cost of trying to use a standby system, or be able to rectify the faults in real time. So if there are less amount of faults, our system tends to become more efficient. So when we discussed in the previous slide, I said that there are only two things that are really important when it comes down to infrastructure. One is efficiency. So whatever is up and running should continue to be up and running for the prolonged interval of time. So for that, I need to reduce the energy usage, and there are solutions to do that. Moving further, we can have IoT based sustainability through climate resilience. So monitoring of air quality inside a building, allowing the traffic flow in and out of the building, can reduce the total amount of pollution or the indicators of climate change when it comes down to smart buildings. And finally, the improved quality of life. Okay, so this improved quality of life is going to be achieved only if we are able to control these three factors. Fine. So coming down to the case study of smart buildings, how at all are we going to control, or how are we going to control the emissions, or the actually statistics say that about 37% of the carbon emissions are only through smart buildings or buildings. So we need to reduce it to a very lower level, so that we are able to implement this sustainable infrastructure through IoT applications. So these are just how at all an IoT sensor can be used to monitor multiple parameters. We know that there are automated lighting systems which wherein the lights turn on only when the room is occupied by a person. So these are small things which are basic as they appear, but they are really essential when it comes down to saving of energy. So if we are talking about of optimization of the building systems, we need to have data analytics, because it needs to collect data, and then only it will be able to regulate how the ventilation, how the AC, how the heating, how the lighting is going to be working. So with smart buildings incorporating these data analytics based IoT solutions, statistics or literature say that there are more than 30% energy savings for building owners. So IoT comes up as a very promising solution for smart and sustainable infrastructure. This slide just gives a schematic. What we see out here is just a black box of how actually the smart building is going to look like at the more detailed level. And trying to connect it to the architecture, what do we see is that the building is going to be comprising of multiple segments, which has been shown in this architecture of the smart building figure. And they are going to be these buildings or the rooms are going to be operated by multiple devices. Now these multiple devices are going to be connected to a particular relay or a switch, This switch needs to be controlled by a microcontroller board. Now, this microcontroller board is the IoT device that is going to control the operation or the closing of these particular devices, right? Now, this microcontroller board, which is going to actuate the relay, is going to get its input from an analytic server, which is the cloud repository. Who is the one that is going to send in the request is the end user out here. So the end user out here is the one that is going to use the application which is present in the cloud to regulate the functioning of the devices inside his house, okay, or inside a particular room. To enable that, we require a network of devices. We require sensors that are connected in the rooms to detect whether there is activity or where there is presence, or wherever there is a population that is there. This is nothing but the communication. Okay, this portion is the communication which allows these devices which are installed on the physical devices in the building, in the smart building, to communicate or send their data to a cloud server. Okay, so what do we see out here? The user communicates or gets information from this. It's absolutely similar to automated lighting in a room, which we usually see nowadays in smart buildings and hospitals, where only when the occupant is in the room, the light turns on, right? So for that, we require sensors to detect. I require a PIR sensor, or um, I require a sensor to detect whether there is a person inside a particular room or not, and then it has to be fed in or communicated via the microcontroller units through a communication module. These Bluetooth and the Wi-Fi module indicate the communicating environment or the communicating network to a particular repository where it's going to be stored. Now, let's say an office building gets most of its activity starting from 9 o'clock, where so all the lights usually, or all the security alarms are going to become active from 9 a.m. till, let's say, 9 p.m. So at the duration from 9 p.m. to 9 a.m., some of the security sensors, or some of the sensors in the buildings that are not occupied, may be turned off for saving energy. So the essence of having a sustainable infrastructure is to cut down on the energy cost. The other diagram is the circuit diagram. So this is the most abstract view of how a smart building is going to look like. This integrates the components, or the three tier or the four layer architecture that I discussed. And to detail it further, how the circuit is going to be looking like is the figure 2 that is shown in this slide. So these relays are going to be connected to the sensors that are installed on the physical devices. They are going to be controlled via main controller that we discussed in the architecture. And this controller is going to communicate via some communicating network, okay, which may be wired or wireless. Okay, the ESP8266 out here is a device that enables it to communicate via the internet, and it is also connecting the other sensors. uh, for example, this MQ135 is a gas sensor that detects the amount of CO2 levels in a particular room. The CO2 level decides, CO2 is a parameter that defines the amount of heating or cooling that is going to be required, which inherently again is going to be turning on the air purifier or the AC. This is just one example in this particular unit of n such devices, multiple sensors and multiple rooms inside a particular building. This is the analytical part or the algorithmic part of realizing this IoT application. So if we are going to go for a smart building which has been implemented, the process is going to work like this. The first process, again, it is repetitive in nature. It will talk about the sensor data collection. So I've just identified four basic sensors. There can be other sensors also, which send its data to the data processing and analysis unit, which are going to collect the data. They are going to send, this is management. I'm sorry for that mistake in typing. Send data to the building management system or the edge controller, and it's going to apply AI or ML rules to predefined thresholds. For example, if the lux, or if it is an automated lighting, if the lux is less than 21, it's going to just turn on the light. So it's a simple if then else rule. So this decision making is inherent. So this decision making is nothing but an if then else rule. If a particular threshold is validated, it moves to a control, or if it is going to give an error, it gives a feedback. It depicts to the end user as to what are the actions that have been performed. Okay, so if there is a particular threshold that has been violated or validated, it will, for example, it will turn on the lights, it will adjust the heating, ventilation, and the AC system, right? If daylight is there and you do not need lights, it is going to dim the light. So these are certain examples or instances of actions that are going to be performed. Where is the end user sitting? The end user is sitting at this monitor. So we require a dashboard wherein the user is going to feed in an input. Let's say that it is a, why at all this is required. This is a simple machine to machine communication, right? I have just written an if then an else rule. Let's say that today it is raining heavily or there is no sunlight, and this our system has, on the basis of AI and ML rules, it finds that okay, if it is 8 a.m. in the city of Ranchi, then the sunlight is going to be appropriate and it is going to automatically turn off the lights. Okay, but dependent on the environment. That's why I said perceiving the environment is really important. I need the user intervention that is able to undo whatever decisions the machine has taken. So this end user basically is going to have the veto over the functioning of the machine. It can rewrite the statements, or it can override the commands that are automatically going to be generated dependent on the rules that we had written for in our decision making model. Okay, so this is the process of a smart infrastructure. Now coming down to one particular, I said I'll be focusing on only one segment of each part. So if I talk about of smart and sustainable infrastructure, one very important aspect, I'll be discussing two things. One is our the infrastructure and predictive modeling, and the other is a very important terminology that has come up is digital twin. So I hope I am able to complete that. So when we come down to predictive maintenance, this is again the four layers of IoT. So I'll just be going about on it fast. So we have the data sources, we've got IoT sensors, and we know what needs to be monitored, right? We have historical performance records. It gets stored into the database, okay? And on these are the processes that are usually followed for any AI ML before we actually perform any analysis. The data is cleaned and you do a feature extraction, and then only you run your algorithms. Then we come down to what is most important in context of sustainability is that we do a predictive modeling. So this predictive modeling is something that will lead to, let's say, reduced energy and water wastage, because I know what is the amount of usage on the basis of the machine learning model or some simulation that I done. So there are multiple models that are available for predictive modeling that can be used for sustainable outcomes for a particular infrastructure. Now, this is a very generic diagram. It is applicable to almost all IoT applications. I cannot say that it is specific to only infrastructure management. These are the basic steps that we follow for predictive modeling. Okay, so now coming down, we are coming towards the end of our talk. So coming to the challenges, what will be the challenges? Because we need a network, connectivity is always going to be an issue, usually in remote areas or in dense urban areas, because then we are going to have reflection, refraction, and it's going to have interference. Data management and analytics, because a sensor is going to create a very huge amount of data, and that's why big data comes into picture. The management and the analysis is not a very easy task, and that too we want it to be done at a real time speed. So achieving this is a challenge. Then we come down to an electronic waste. We say that everything can be uh, automated. So, but automation is always going to have battery supply. It is going to have multiple electronic devices. So, electronic waste is a very important or a very major challenge that we are going to face. And obviously, we are going to have policy gaps and skill shortages, so that we are able to have a framework, or we can have a certification for a particular IoT application that is still absent. Now, what are the strategies to overcome the challenges? Because connectivity is a problem, we need to optimize the connectivity, because data processing is going to take a large amount of time, and pushing data from the device to the cloud is really not going to work. So we need to implement an edge and fog computing that is closer to the source. So it requires a reduction in the bandwidth requirements. We need to promote circularity. Now, circularity, I'll just say one line because this relates to circular economy, is that uh, it is focused on eliminating waste and pollution by keeping materials and products in use for as long as possible, with the help of certain activities like reuse, repair, recycling. We all know what is circular economy. Okay, it is not related to IoT per se, so I'm not discussing it in detail. And obviously, we need to have policies for justifying our sustainability goals. Now, for in context to IoT, I can only work with connectivity, and I can work with the amount of data processing. So I've just taken those two challenges that can be solved with the help of IoT applications. So the first solution to challenge of optimizing connectivity is through hybrid communication technologies. So we've got multiple ways in which the end devices can connect to the cloud server. It is dependent on the range that we cover. So among them, I've just identified a few. We need to choose between the right technology based whether our application needs lesser latency, whether our application can run with low bandwidth, or it can run with less energy. As an example, a low latency application will be a fire alarm, because I cannot wait for a delayed response from the cloud server. Neither can I depend on the network to actually process the data back and forth to the cloud server to the device. Okay, so here my bandwidth requirement is really less, but I wanted the processing to be really fast. So now I'll have a different category. I'll need to choose between a low pan network or a 5G or a 6G network. Okay, when it comes down to bandwidth, let's say it is a traffic monitoring type of an application wherein we want to have camera based sensors. So camera based sensors are not going to generate textual data, they are going to generate image based data, and images are going to be if they are going to be transmitted, they'll require a higher amount of bandwidth, and we cannot have a low bandwidth network to facilitate it. So in this case, we cannot go in for a LoRa ban or NB-IoT. They cannot be used for a traffic monitoring application. So we need to have hybrid communication technologies for optimization. Next, we move down to A network topology optimization. A lot of work has been done for topology optimization, wherein we have multiple ways to achieve the best way to communicate with the minimum amount of energy expense. So, maximum coverage, minimum infrastructure cost can be achieved if we have an efficient network topology. The third solution is if we are moving the data processing unit closer to the end device, because whenever we are talking of communication, its simple laws of physics are going to rule. It is going to be an EM wave propagation. So the distance and the speed is going to be identifying the time. So if I pull the server closer to the end device, obviously it is going to give me a faster response. So the responsiveness can be for critically important structures like traffic signals, like smart building security. I need to have a edge or a fog computing infrastructure in place. The fourth solution is having an AI-driven network management, wherein we have predictive analytics for traffic load balancing. We know that, okay, most of the traffic is going to cross one particular area in the morning. So we need to have that sort of a load balancing. The other type of load balancing out here is the data load balancing. Traffic does not only directly mean the I was just trying to relate it to the physical traffic. Similar to that, the data traffic is going to be moving across the devices. So if all the devices start up and start communicating, it's going to congest the networks. So network congestion can be optimized if we have predictive analytics based traffic load balancing. Okay, so which routers are going to be turning on and transmitting, connecting to which type of data, end nodes is going to be defined. Okay, similarly we can have adaptive routing used by reinforcement. We can use Bayesian belief networks for network connectivity. Okay, finally energy efficient protocols and redundant paths to ensure fault tolerance and reliability. Okay, so this is just the diagrammatic representation of LoRaWAN architecture and narrowband architecture for a smart city, wherein the LoRaWAN is the characteristics of LoRaWAN is that it allows you to have low data rate, minimal power. It also allows you to go up to ranges like 750 kilometers, and it's a wide area network. So because of its facility to deeply penetrate inside the building, it uses geolocation for free. It is a license free spectrum. It usually is the best solution for a smart infrastructure. Narrowband is again a good solution for a smart infrastructure for a smart city, because it is based on already existing cellular infrastructure. So you do not need to install multiple devices to realize it. Okay, I think my time is up, Tiwari sir.
Yes, sir. Yes, ma'am. Yes, ma'am. It's
Sure. So
11
I'll
minutes
just
over.
conclude on the
But
future of.
anyway, you can take 2, 3 minutes, and if you
Yeah,
can.
I'll just conclude.
Okay, okay, ma'am.
So coming down to the future, I'll be leaving the discussion on digital twins. So basically, what is the future of IoT and sustainable infrastructure is that we can incorporate AI based solutions and digital twins for predictive maintenance, optimization of infrastructure, and we can have adaptive infrastructures for climate resilience, wherein we can use sensors to control the ambience of a particular building, renewable energy resources where we can have solar powered and other resources to manage the particular services inside our application, and finally at the whatever are the global goals, we need to achieve that. So I think I can conclude with this slide. I hope whatever I can accommodate a few questions.
Yes, dear participants, if you have any question, you can ask. Ma'am, I want to ask one question. Like,
Yes,
my field is RF circuit design. Okay, ma'am.
yes,
And I'm using I3D, HFSS, CST. Okay, these software tools.
Okay. Yes.
How how I can align with this AI things? Like
Sir,
any
yeah.
structure is there. Although
So
Nisa madam,
actually, with
Nisa madam,
HFSS, हाँ जी बोलिए sir.
yes ma'am. Nisa madam told me several times that this is your patches. Okay,
हाँ.
in the top layer, so you can use something uh, 0101. But I didn't do that those things, ma'am.
Okay. Actually, the software that your CST Microsoft Studio and that HFSS that you are mentioning, they
Yes,
generate data, sir. What you
data
get
set.
is
Yes.
either waveforms or you get textual data of those waveforms. So
Okay.
whenever I have and you whenever you are working in this simulation environment, for one fixed simulation environment, you can generate multiple data by tuning in the parameters and running it for multiple instances.
Got it, ma'am.
So once you populate the data, you generate the data set on the basis of which you can make predictions, like if this is the particular, if x is the parameter that is going to lie between range 1 to 10, and
Hmm.
y is the parameter that lies in the range of 20 to 50, then the probably the output that it is going to generate is going to be you can validate it with your simulation results. So
Oh,
next time, so with Nisha ma'am only we were working on this, that rather than testing for electromagnetic interference, given the voltage and the current fields, you can predict what is the amount of interference that you can expect at a particular distance. So just by running in the simulation and populating the data, AI can work typically with if you have data and you will be able to have some sort of interpretation using that data. So in that way, you can use your HFSS and the simulation results that you obtain.
okay, ma'am.
AI
Thank you.
models can be developed on
Yes,
that.
yes, 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 ma'am. Any participants, if you want to ask the question, you can ask here. Otherwise, you can write in the chat box also. Or else, what we will do, we will share ma'am's mail ID. You can ask question after this session, or anytime if you wish, you can just mail the content of or questions to ma'am. Definitely, ma'am will give the answers. With this, I'm giving to my co-coordinator, JP Singh sir, and he will conclude the session.
Thank you, ma'am, for your very nice presentation. With this, we can conclude this session and proceed for the next session, that is at 3:30. So, candidates kindly move and log into that session.
Okay, should I stop, ma'am?
Okay, thank you. Thank you,
Hello.
sir.
Should I stop, ma'am?
Should I stop, ma'am?
Hello,
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 hello.
Itu ma'am?
Itu, ma'am?
Yes, yes, yes. Thank you. I'll just leave the meeting.
Okay,
Thank you.
okay. Thank you, ma'am. Thank you.